gas law for a different variable. It says, what volume in liters is occupied by 35.4 grams of C2H2 at 814 millimeters of mercury and 63 degrees Celsius? So I have grams, and I can then find moles and use the ideal gas law. And let's see. And one thing I'll point out about this is, so the ideal gas law works for all gases. So, and what we will see is that the only place that the actual identity of the gas comes into it is when we use the molar mass. So, but the ideal gas law works for all gases, which means, and that's why we don't even have to identify the gas here. And that will happen sometimes. But for now, we have, let's see, we have grams, so we can find moles. Moles is what we need to plug in here. We have a pressure, which we have to convert into atmospheres. And we have a temperature in Celsius, which we have to convert into Kelvin. So let's go ahead and do that, and then we'll plug everything in. My millimeters of mercury are converted into atmospheres using 1 atmosphere equals 760 millimeters of mercury. (814) divided by 760. No, you can't even see it. There we go. 1.07 atmospheres. And temperature, so Kelvin is going to equal degrees Celsius plus 273. (336 Kelvin). So let's see, I've got my temperature in Kelvin, I've got my pressure in atmospheres. Let me turn my grams into moles so I can get my moles for this equation. My molar mass here, 12.01 times 2 plus 1.08 times 2. 26.04 will be good for that. (35.4) divided by 26.04. I'm going to go to 1.36 moles. And now I think I've got everything plugged in. I'll do this with the numbers plugging in method, and then, so just to counter it with the last example that I did. So I have PV equals nRT. My pressure is 1.07. My volume I don't know, so that's my unknown. My moles I know. My R value I know, 0.08206. And those are units of liter atmospheres per mole Kelvin. I don't know if I've mentioned this before, but I heart units. And temperature is 336 Kelvin. So now to solve this, I divide both sides by 1.07 atmospheres. and my volume. .36 times 0.08206 times 336 divided by 1.07. I get 35.0 liters. And that's a fine way to leave your answer, liters. You could also say liters of gas or liters of C2H2, but on your problem statement it says you're just going to enter the number 35.0 into the homework answer. Any questions about that?
Yes, Professor, quick question.
Yeah.
For the 26.04, where do you get it from?
This is the molar mass of C2H2, so I got it from the periodic table.
Okay.
2 times carbon plus 2 times hydrogen.
Okay, thank you.
Yeah. And actually, let me just record another minute or two. So what we've said so far is we've used the ideal gas law for C2H2, which is acetylene, a welding gas, and we've used it for oxygen, also a welding gas, incidentally. You can get bottles of oxygen as well. And the equation was the same. And that's what I mean by the ideal gas law works for all gases. And I talk about this in the lecture outlines, but I want to state it here. So basically, our picture of a gas is that whatever the gas is, whether it's oxygen, which would look like 2 little O's bonded together, or C2H2, there's tons of space for that gas. And it's flying around very quickly there. There's another oxygen. And so the reason that all gases act the same for the ideal gas law is that they're so far apart that attractions between the gas molecules are negligible. So far apart that there are negligible attractions between, that's my abbreviation for between, gas particles. And in chemistry, what we will see is that one of the main things that sets molecules and atoms apart from each other is how they attract one another. So if you take those attractions away, then all gas particles, all particles are the same. And that's why the gas phase is the only one we really talk about. Well, I guess we did aqueous phase as well. But in the aqueous phase, you had aqueous particles that were surrounded by water molecules, and those aqueous particles were far apart as well. But we will not talk about theories of liquids, and we will not talk about theories of solids because they're just too complicated for us right now. Anyway, so our picture of gases is as being so far apart and moving so quickly is why we can use this equation for any gas and why any and all gases act the same. Thought I'd throw that in there too.
What did you say? You said C2H2 is a what type of gas? What you call it, saline?
Oh, acetylene.
Acetylene.
Yeah, if you've ever used or heard of an acetylene torch for welding.
Are we expected to know that?
No. So certainly this semester there has been a lack of emphasis on being tested on nomenclature. And so that will continue. But I put names in sometimes just in case. So I don't know if anybody in the course has done welding before using acetylene, but no, you don't have to know.